here are events which we have already detected so far and analyzed completely. That is, till the first segment of the fourth observing run, we have detected 218 events, which is reported in the gravitational wave transient catalog by LVK. And these blue dots are basically the gravitational wave events. So as you can see, these are the component masses, and then they give rise to another remnant black hole. So each of these lines corresponds to total 3 black holes. And you can see that the detected black holes ranges from about, say, 2.6 solar mass to above 200 solar mass. So we have found black holes in this region, and we have also found different neutron stars around, their masses are roughly about 1.4 with some error bar here and there. And the rest of this, so these red dots are the black holes that has been detected with electromagnetic observations. And the yellow dots are the neutron stars, which has been observed with the electromagnetic observations.
So the x-axis has no significance, right?
No, x-axis has no
Just
significance. You can orient it as an increasing mass, and yeah, just so it looks good. Exactly.
Sorry, where are the like LVK neutron stars?
LVK neutron stars are these orange ones. So this one.
Oh, so I think the color, yeah, okay, brown
color,
and
yeah.
those are orange.
Yeah. Right. Okay. So what we do when we basically analyze the data, there's a kind of flow chart which I will tell you briefly. I will not go into the details because we probably don't have time. And so what we do when we observe when the detectors observe, we get a chunk of data, which is as a function of time. Now we create a template bank. What do I mean by template bank? Template bank is basically a set of waveform models which are defined by the masses and the spins, maybe eccentricity and etc. So we create a template bank, and then we cross correlate all those waveform models with the data, and we find the triggers. Now we define some quantity called ranking statistics. So this ranking statistics, if it crosses some threshold, we call it a detection. So that's how we detect different events in our detector data. And then once we get all these events, we use different set of waveform models with various physics encoded within the waveform models for the parameter estimations. And finally, once we do all this procedure, we come up with a gravitational wave catalog. Now, till the third observation run, LIGO has made their data public. So till now, there has been 3 gravitational wave catalog. One is, of course, by the LIGO-Virgo-Kagra collaboration, what they call it as Gravitational Wave Transient Catalog, GWTC. There's another one, which we call it as Open Gravitational Wave Catalog. So this catalog was made by the Compact Binary Coalescence Group based in AEI Hanover. But unfortunately, that group is not there anymore. So different people have moved to different places. So I don't know if there will be another Open Gravitational Wave Catalog or not. And the third one is a catalog put up by the IIS Princeton group. What I have shown here is the template bank that has been put forward for the search by different groups. So this is the template bank that we used to create the Open Gravitational Wave Catalog. And the yellow dots are basically our detections. This is the template bank by LVK collaboration for their 4th observing run. And this is the IAS template bank. Now, using all these template banks, all these 3 groups made their catalog public. So all these 3 catalogs are very similar to each other. There are small differences in this catalog. For example, Open Gravitational Wave Catalog reported total 94 compact binary mergers till the 3rd observing run. Now, they have reported 7 new binary black hole mergers, which were not reported in the LIGO-Virgo-Kagra catalogs. But the broader findings were more or less similar. You can find the data release for this Open Gravitational Wave Catalog in this GitHub link. You can go and check, and even you can use their open the library which they use for search and the parameter estimation, you can do it yourself with open data. And then the IAS people put their catalog public, and they also find 6 new binary black hole mergers in the data, which were not reported either in Open Gravitational Wave Catalog by the AI Hannover group or the Gravitational Wave Catalog put up by the LIGO-Virgo collaboration. This is a plot which shows the different detections. So lighter gray blobs are basically reported by the LIGO-Virgo collaboration. The darker blobs are reported by AI Hannover group, that is Open Gravitational Wave Catalog, and the colored ones are what reported in the IAS catalog. Okay. And yeah, so this is the newest result from the O4A, where the detector ran from May 2023 till January 2024. And they detected about 128 new significant signals from compact binary coalescences. And that makes the number to 218, the total number of detections up till O4A. And this is the detections. So the blue blobs are the detection in the plane defined by the primary mass and the secondary mass plane. And you can see that this is the 231123, which is the most massive detection till date. And I think there was a talk maybe last week or last week about this event. So you know better than me probably. And there were also some important events which I will be using. So I need, yeah, this one, GW 190521. So this is also a higher mass event. The total mass of the remnant black hole was about 150 solar mass or so. I will come to this to a later time. Okay. So now let's move to tests of general relativity using gravitational wave observations. Now there are different tests of general relativity in the literature. If you roughly put these tests in the plane defined by a field strength, which is typically phi defined by the mass over the characteristic length, and the curvature, which is roughly goes as square root of m over L cube, then the gravitational wave events lie on the top right corner, which is extreme curvature and the strong field regime. So you can, of course, understand that this gives a wide and unique opportunity to test GR in the strong field regime. Right. So what we actually do while we say that we are doing tests of general relativity. Now, the different tests of general relativity using gravitational wave observations can broadly be divided into 2 categories. The first one is model dependent test. You can pick your favorite theory, for example, massive graviton theory. You create the waveform model within that theory defined by the parameters within the theory. You match your waveform with the data and you come up with the bounds on the model parameters. That's what you can do. Now the question is, which theory will you pick? Because there are hundreds of theories for general relativity and we don't know which one to prefer. And so I will give you an example. To get a highly accurate GR waveform model, it took almost 40 years. So the trial started around in 60s, and now also the waveform modeling is still going on. So it takes a very long time to really come up with an accurate waveform model to match with the data. So you cannot just pick a model and create the waveform by like this. So you cannot do that. It takes time. But we are currently detecting gravitational wave
Why
events.
it take time? Because of the computational resources?
Computational resources, difficulties in the computation, and yeah. And the second thing is model agnostic test. So we have a GR waveform model. What we can do is we can add ad hoc deviation parameter in those waveform models. We can compare that modified waveform model to our data and can put bounds on those deviation parameter. Now, if the GR is correct, then those deviation parameter is expected to be 0. If you find something else than 0, then you will think, okay, so there is some deviation, and then you basically have to backtrack where the deviation is coming from, and maybe to a particular theory which can give rise to that kind of a waveform model. But I'll tell you, so far GR has passed all the tests with flying colors. Now we will discuss a few of these gravitational wave tests which I have been part of. So there are many tests that people are performing on the gravitational wave data, and in recent times actually it took so much of computational resources. People are thinking of one maybe one test which can summarize all these tests, but there are not any tests that has been developed in those lines. So right now we are performing quite an extensive set of tests of GR. I will be focusing on few of those and give you some results. Before going into the details of the test, the basic ingredients and the most important ingredients that we need is a gravitational waveform. Now, within GR, gravitational waveform can be divided into 3 regimes. The first one is the inspiral, where the two compact objects are far away from each other and orbiting around each other. That part of the waveform, you can use analytical approximation scheme, which is known as post-Newtonian theory, and you can model the waveform in this region. Now, when the two objects merge, that part, you cannot use your analytical modeling, and you have to rely on numerical relativity techniques. The third regime, where the merged object slowly settles down to a proper curved black hole, radiating the gravitational wave, is known as ring down. And this part of the waveform is modeled with the black hole perturbation theory. Now you have waveform in the inspiral regime, you have a waveform in the numerical in the merger regime, and you have a different waveform in the ring down regime. You can stitch all these 3 together to find your complete inspiral merger ring down waveform model. The first test that we are going to talk about is about this part of the waveform. That is, we will do a test of post-Newtonian theory. Now, post-Newtonian theory is basically a mixture of various analytical approximation schemes, which actually relates the radiation content in the far zone to the stress energy tensor of the sources. And the waveform in this approximation can be written as a series in V or V by C. Now, what is V? To the leading order, you can think of this V as a orbital velocity of the reduced mass. But as you go on to the higher order, this notion of orbital velocity actually drops, and you can think of it as just a bookkeeping parameter or a perturbation parameter. So in this schematic structure, what you are seeing is the amplitude is written as a series in V, as well as the phase, that is here I have written as psi SPA. This can also be written as a series in V, which I have shown here. So this is a series in V. As you can see that it's a sum over K, and there's a term called V raised to K. And the different coefficients, these phi Ks, are known as post-Newtonian coefficients. Now, if the underlying theory is GR, then given a mass, spin, and eccentricity, you can exactly compute what are these phi Ks. And if the underlying theory is not GR, then these phi Ks will be different. And you can expect deviations appearing at every phi K order. So what we do is, we add some ad hoc deviations, some free deviations, delta phi K to all these phi K GR. And given a data, we compare our waveform model with the data and try to put bounds on this delta phi K. That is what is shown in this figure. So as you can see as the label, so the first one is delta phi 0, which is a 0 PN deviation. Then there's delta phi 1, which is a 0.5 PN deviation, and so on, 1 PN, 1.5 PN, and so on.
Sorry.
Yeah.
So I thought K is like integer. So what
K
is
is
0.5?
integer. Okay, so this is this is a post-Newtonian notion. 1 PN order means V square over C square.
Oh,
So 1.5 PN is V by C.
I see. Right.
So 0.5 pin is a V by C correction. Right. So this blue diamonds, yes. So the blue diamonds are basically the bounds on these delta phi's from GWTC3. That is all the events detected so far up till third observing round.
So sorry.
Right. Yeah.
So in the left-hand side plot, I understood your, what you call as delta phi 0 or delta phi 1 is the V by C order correction.
Right.
But that is for the,
Phase.
yeah, that's for the phase. Now, so, but that's which of the post-Newtonian coefficients? Which was this is one of the PN coefficients or the corrections in
So
all
delta phi 0 is the 0 PN deviation to the 0 PN coefficients. Delta phi 1 is the deviation to the 0.5 PN coefficients, and so on. So these are the at different post-Newtonian orders. So what we basically do is, ideally you will say that you will deviate, you will vary all the delta phi case till 3.5 PN order. But
Yes.
till 3.5 PN, there are at least 9 of such delta phi case. Now, if you add those 9 parameters along with the GR parameters and masses and
It's
spins,
lot.
lot of parameters, you will not get any meaningful values on these delta phi case. So what we do is, when we vary these delta phi case, we vary one at a time.
Yeah, that's what I was asking.
Yeah. So the expectation is, even if there is a deviation at higher PN order, it will show up some signatures on the lower PN order terms. Yes. So to your question, we try to see that how we can improve the measurement, or whether there is a way to vary these parameters all at a time. We can only do that if we have a situation where we are seeing the same system in the LISA band. So suppose we are seeing the Inspiral in the LISA band and the merger in the third generation, or the Cosmic Explorer or Einstein telescope band. So the same event we are seeing in the LISA band as well as the Einstein telescope band. In that cases, we can vary several of these delta phi case at a time and get bounds on those parameters, which is kind of reported in this.
What pin is using?
Right.
So why do in case of Lisa you can use the same thing for higher parameters?
No, I don't get your question.
No, you were saying multi-parameter bound can be done to Lisa.
LISA as
And-
so LISA and C together. So if we are seeing the same source in LISA as well as
Right.
C,
So what
then-
do we change there? That you
so we are
will be able
getting
to-
more
data.
more information.
Yeah, so you have to constrain parameter. The more data you have, you constrain.
Here also you are using two
Right, here also
detectors.
we are using different detectors, 2 or 3 maybe at some cases,
Correct.
but all of them are observing the same frequency.
Frequency change. You have to broadband.
Frequency change. So
Broadband.
LISA works in the frequency band, say 10⁻⁴ to 0.1, and C operates in the range of 1 hertz to say about 1,000
So
or
they
500.
should have different wavelengths. That's
They have different
multi-wave
frequency
and
bands that
DW.
they are exactly. Right. Okay. So now, as I said, that these post-Newtonian coefficients, they do not really have a physical meaning. So what we thought, maybe we don't add the deviation at the level of post-Newtonian coefficients, we add the deviation at the level of multipole moments. The post-Newtonian coefficients can be computed using the multipole moments. So then we add the deviation at the multipole moments. There are total 7 multipole moments that appears in the 3.5 PN gravitational waveform. So we add 7 parameters. What we achieve by doing this is we can simultaneously and uniformly use the deviation in the phasing as well as the amplitude. So in the previous case, we were just adding deviation parameter in the phasing. Now, if we wanted to add some deviation at the level of amplitude, then we had to introduce another set of parameters, which we do not need to do in this case. So we recomputed the gravitational wave phasing till 3.5 PN as well as the amplitude. And then we took 2 simulated events, which is a lookalike of GW 1904-12 and 1908-14, and find the deviations, bounds on these deviations at different, for different multiple moments. So delta mu2 is basically the deviation of the quadrupole moment, mass quadrupole moment. Delta mu3 is mass octupole moment. Delta epsilon 2 is current quadrupole moment, and etc. So this is another test known as test of post-Newtonian multipolar structure. This we started developing in my PhD, and it's still going on.
So that LIGO Aundha, you mean the Indian?
Indian, LIGO India.
Like what?
Aund.
So Hanford, Livingston, and then there's
HLA.
Aundha.
So
How-
some-
Yes.
somehow the higher order bounds are going in.
I was thinking that somebody should ask these questions. So right, so higher order, as you go to higher order terms, so as I said, that those are the higher order terms. That means they come up with a prefactor of V by C compared to this delta mu2. So their contribution to the gravitational waveform is much less compared to the leading order term. So that's why their bounds are kind of worse. The measurement is worse on them, on their estimation.
Larger means worse.
No. I thought this is the down line is the zero.
Ah,
Zero
no,
is the not that one.
no.
These are simulated events,
Yes.
and so those triangles and circles and stars are different kinds of simulations using all these.
No, so the
For-
difference in these things, they are basically the different combination of detectors.
Yes, that's what I'm saying. So those are the combinations.
Yeah, of the detectors. So HLA is the LIGO Hanford, LIGO Livingston, and LIGO Aund to measure the deviation. And then this is, so 40 LA is basically the CE Washington, Cosmic Explorer Washington with 40 kilometers arm length, and LIGO Livingston and LIGO India.
So then the question is, I think, related to what Shomodeep asked, is that when you see the deviations in these multiple moments, there is a trend. Do we expect that trend to see? Because we can clearly see that it is sort of increasing. I mean,
Yes,
yeah, I mean,
so the quadrupole
pretty-
moment, exactly. So the quadrupole moment actually appears at the leading order term.
yes,
And then octupole moment comes at 1 p.m. order.
yes.
So as we go to higher multiple moments, they comes to the higher post-Newtonian order as well.
yes.
That's why their contribution to the whole
Yeah, that's what I
waveform-
understand.
Right.
But what is interesting to me is that there is a trend. I think
No,
it
it's
seems
that
like
higher order terms are less bound. That's
Yes, the bound on them is worse
Yeah,
because
that I
all. So
understood.
those are upper bound.
those are upper bound,
So
exactly.
it has to be less than that.
Yes.
So if you have a higher order, they contribute much less to the end,
To
then
the
they are
signal.
much less bounded. That's all.
That's
Yeah,
all.
I mean, that is fine, but what I was wondering is that why do I see that there is a pretty specific trend? I mean, if I see the red ones, there is a flatness and then they kind of pretty linearly in a log scale change. So I was thinking, is it any significant thing or it's just a coincidence?
It's
The
not.
trend. I mean,
Yeah, so it's,
It
I
could
would
be,
say
it could
it's a-
be larger, contribution is fine, but there is a
Yeah.
flatness and there is a trend. For, I think for all the detectors, I kind of see that. But is it, maybe it's the log scale or something?
I think it's really a contribution that they give to the waveform model. So if some terms gives a better contribution, then you will measure those terms in a better
Okay,
format.
so this one.
Yeah. Okay, so now I will move over to a different test, for which we will be using the ring down part of the waveform. That is known as black hole spectroscopy. Now, what do I mean by black hole spectroscopy? The ring down part of the waveform can be modeled using the quasi-normal modes of the curved black hole. So basically the ring down part is modeled with the linear black hole perturbation theory, and you can write the waveform as a sum over simple damped sinusoids. And the radiation pattern goes as the spheroidal harmonics. So the gravitational waveform that you can write is a sum over all the quasi-normal modes. So every quasi-normal modes is denoted by 3 numbers, L, M, and N. SLM is the spin-weighted spheroidal harmonics, and the amplitude ALMN is for the particular quasi-normal mode, And it is also defined by the frequency, complex frequency of the quasi-normal mode. Now, the complex frequency is a function of the frequency of the gravitational wave, F element, and the damping time of that particular mode, tau element. This frequency and the damping time is uniquely defined by the mass and the spin of the astrophysical black hole. Now, suppose you detect one quasi-normal mode in your data. You can use your model and can identify what is the remnant mass and the spin of the object. Now, suppose you detect two quasi-normal modes, more than one. That is what we call it as black hole spectroscopy. If you detect two or more quasi-normal modes, the first mode you use to measure the mass and the spin. The second mode you can use to test the no-hair theorem. So you can ask whether there is an extra hair present in the data or not. So that's what we can achieve by doing black hole spectroscopy.
These are multiple moments. I mean, these are like okay, multiple quasi-normal modes.
Quasi-normal
That's why
modes,
there are
exactly.
three indexes.
Indexes,
elements.
yes, yes. So in 2005, I think there was a paper by Emanuele Botti, Vito Cardoso, and their collaborators. They predicted that black hole spectroscopy will only be possible with the LISA detection. But with a more improved population model in 2019, Cabero et al. Predicted that we at least need LIGO Voyager-like sensitivity to detect one event per year, where there will be present more than one quasi-normal mode. And to our surprise, we actually detected one massive event, GW 1905-21, which provides us an opportunity to detect more than one quasi-normal modes. Now, this event is quite controversial, I would say. So let's look at the mass plot. Let's look at the component masses of this event. So this is the component mass plot reported by the LIGO-Virgo-Kagra collaboration. And as soon as LVK made their data public, there was another group, Alex Nitz and Colin Capano. They performed a similar analysis with a different IMR phenom XPHM model. What they found is, they found this blob as reported by the LBK collaboration, but they also found a secondary blob which signifies a higher mass mode. That means this blob actually tells us that there could be more than one quasi-normal mode present in the gravitational wave data from the ring down. But later there was another group who performed the same analysis with a more updated Morphonomics PHM model. They did not find a very high mass ratio mode about 10, but they still found a second blob where the mass ratio was roughly about 6. Okay. So there are other scenarios that has been proposed for this GW 1905-21. So this paper, they have discussed that maybe this event can be very highly eccentric compact binary mergers, or with a more exotic scenario where these people suggested that this event can be even a scattering of hyperbolic merger event. But in all these events, if the two black hole has merged in some way, then the ring down has to happen. So we performed our data analysis after the merger. Here, what I have shown is basically the white end strain as a function of time. And on the right side plot, the strain is plotted as a function of frequency. So if you look at this plot, what you're basically seeing is a peak in this frequency band. We call it as A. There's another peak in range B, and range C is basically the noise. Before going into any modeling, we tried to fit the data with two simple damped sinusoids. We don't know anything about the Kerr black hole or Kerr spectrum. We just fitted the data with two damped sinusoids signified by frequency and the damping time, and we plot our result. So we found a blob in range A. So the frequency is about 60-ish. We found a second blob where the frequency is roughly about 90 to 100 hertz. Now, if we consider a Kerr black hole and we say that the first blob corresponds to the quasi-normal mode, which quasi-normal mode signified by L equal to 2, M equal to 2, and N equal to 2. Then the second blob actually coincides with the mode 330. So we basically detect a second subdominant mode 330 in this event. And more rigorously, after doing our agnostic search, we again search our data considering different combinations of Kerr quasi-normal modes. So we have an exhausted list of combination of different quasi-normal modes, but we don't show it here. We have just shown 4 combinations, and we find that after 6 milliseconds or so, we see that this combination 220 and 330 has a higher base factor. That means this model is much preferred by the data. So now we can confidently say that we have detected a strong subdominant mode existence. As I was saying, that if you detect 2 or more quasi-normal modes, we can perform a test of no-hair theorem. How you can do that? You can basically add some deviation frequency and the damping time to your secondary subdominant mode. So you have one mode 220, which has frequency F220 and damping time tau 220. You have the frequency and the damping time for 330, as well as you have some delta F deviation to the frequency and the damping time of the 330 mode. And what we find is delta F 330 and delta tau 330 is consistent with their values being 0. So there is a spread in delta tau 330 or delta F 330, but their value 0 is inside our posterior. That means that means this event actually passes the no-hair test.
So, and also the two groups, there was a conflict between the, findings of two groups that one you showed.
Right, yeah.
So now from your analysis, could you reconcile like why, because you do find the second P,
Yes,
which these guys didn't find.
yes,
Maybe
exactly.
people
I
didn't
don't
find.
remember if I have no, I don't have the mass ratio plot. So in presence of this 330 mode, you can basically backtrack what could be the mass ratio of the initial two black holes. But it was quite, because the sensitivity to the 330 mode was very low. So the posterior on the mass ratio was not very narrow, it was wide, but we do find that mass ratio 6 within the posterior.
So that thing, but then any reason was found why LVP couldn't detect it? Is it sensitivity or? Because
Not
the other group did, right? And you said that there was a 6 kind of mass ratio
Right.
that they got.
So there is an ambiguity about the fact that we are fitting with a linear perturbation theory. Now, where that linear regime actually starts after the merger, we don't know. Based on our knowledge on numerical relativity waveforms, people say that after 10M, you can fit your linear black hole perturbation theory and get the quasi-normal modes. Now, that 10M corresponds to about 6 or 7 milliseconds for this DW 190521. Why LIGO did not find, I would say they have combined all the quasi-normal mode to search in the data. But if you start adding all the quasi-normal modes, you basically increase the number of parameters. So you won't get any meaningful results on all the parameters. We just happen to be the case that we first started with this 220 and 330 combination, and we got it.
What was the color code in the previous plot? Yeah.
Oh.
Yeah.
This one?
What does the color mean here?
So this is the posterior. I mean, the lesser significant numbers will be here. So that depends on the likelihood value. We haven't shown it
That's the
here.
probability distribution.
Probability distribution.
But
Exactly.
it's not related to any sort of intensity or anything.
No, no.
Because you are saying that this is a subdominant mode, but it
Yes.
looks much prominent in the detection, but that's the
No,
probability.
because you see, it's a widely spread. Compared to this is very narrowly picked. So sensitivity for this mode is more compared to this one.
And then I can see some green, red
Yeah, so
What are
this is
those?
green are expected 440. So consider
Oh,
this as a 2 to
rather
unexpected ones will come here, but we don't really see anything in those regions. Okay. So as Shri Chaitanya was pointing that we don't really know where exactly our linear regime starts. There is another event. So I think no gravitational wave talk can be over without mentioning this GW 150914 at least once. There was a funny incident. I was listening to an interview by Professor Rana Adhikari, and he was saying that this event is so perfect that they even thought that it could be a made up event. It was not real and it was made up. But I think after that, they rigorously analyzed the data and confirmed that it's a real detection. So this is
The universe was very kind to
yeah, exactly.
Very kind.
Also, LVK was very careful to report the first event. Yeah, right. So 150914. Now, as I was saying that you cannot fit your linear perturbation theory very early and very near to the merger. There, your waveform is not even valid. Now, there's one group, this PC et al., they actually fit their quasi-normal mode waveform model to the gravitational wave data for 150914 at the merger. And they found two modes. One is the quadrupolar 220 mode, and the second one is associated to the overtone of the quadrupolar 220 mode. So then people were not really happy and say that you cannot fit your linear perturbation theory to the at the merger because there your waveform is not even valid. So that controversy is still there. Some people really believe that we have just simply fitted our data and found the existence of 221. We are not asking for anything more. But people say that you are fitting to, I don't know what, your waveform is not valid. So that's the basic controversy. But then in the fourth observing run, this January, actually, this event got detected. Their masses are very similar to 150914, but with a very high signal to noise ratio in the detector. And the mass posterior you can see here. So the blue one is basically the GW250114. And since this event is also very similar to 150914, you can perform the same analysis of finding the quasi-normal modes. And what LBK found is that for a fair enough time, they found the existence of the 221 mode along with the 220. So now we can confidently say that we have also observed the overtone associated to the quadrupolar quasi-normal modes. And there's also a funny story associated to this event. For this event, LIGO made their data public in sometimes in August. Even before they made their data public, they just after detection, they put up what could be the masses and the distance and etc. With that information, the CBC group in Syracuse University, they simulate an event like GW250114, and they even find the existence of this overtone even before the LVK reported the results.
So they
Right.
are the simulated input included the what they
Yes,
did.
yes. So given a mass ratio, you can guess what could be the what could be the quasi-normal modes.
Be able to get there.
2 to 1. Yeah, exactly.
Theoretically.
Yes, yeah. Right. So there is another test that I would like to mention briefly, which is Inspiral merger ring down consistency test. So till now, I have talked about three tests. One is based on the Inspiral part. The second one was based on the ring down part. And now this Inspiral merger ring down consistency test is basically you divide your data into two halves. One is which consists the Inspiral part, and the second one is the merger and the ring down part. Now you estimate using your waveform model, so what would be the parameters from this Inspiral part? And similarly, independently, you measure the same parameters from these part of the waveform. And you can compare these two parameters to see the consistency between different waveform modeling techniques. And I think this is kind of a routine test in these days for all the gravitational wave events. And for most of them, they are consistent with the pre-merger and the post-merger phases. Yeah, this is the same thing that I was mentioning. And yeah, so you can pose the same question, that consistency test, as a test of black hole area theorem. I think this was first developed by the AI Hanover group, and LIGO has started using this test for their data as well these days. So what we see is, so from the Inspiral analysis or the pre-merger analysis, you can compute the component masses and spins and etc. And from that, you can get the total area of the two black holes. And then you can compare it with the final area of the final remnant black hole. So that's if the initial area AI is much less than AF, the final area, you can say that the event has passed the black hole area theorem. And so this is the newest result from GW2114. And you can see that most of the probability distribution lies above the fractional area being 0. So beyond this, this is the region which is not allowed by GR, and this event actually passes the test of black hole area theorem with flying colors. Right. So the story so far, we have talked about the Inspiral test. One is parameterized test of post-Newtonian theory. The second one was parameterized test of post-Newtonian multipolar structure. The third test that we were discussing is the ring down test. And the fourth one is Inspiral merger ring down consistency test, or the test of black hole area theorem. So yeah, to summarize, I would say broadly, there are three questions that we are currently asking. That what is the nature of the theory, whether it's Einstein's GR or something else? The nature of the black hole, whether the astrophysical black hole do have extra air or not. And then the third one is astrophysical and cosmological implications, for example, measurement of Hubble constant, population models, lensing of gravitational wave events. Right. So, thank you all for.
Okay, questions? Okay, let's see, ma'am.
Mine is like, okay, actually I have two comments. I'm gonna go for one first.
Right, yeah.
So is it okay to tell that so far, whatever studies we have done in the GW regime, GR is like with flying colors.
Yes.
So you have no reason to not accept GR happening
Yes.
from what we find in GW.
Yes.
So that was my.
But one thing is there that what I think is the kind of waveforms that we are using is basically based on GR. So the kind of deviation, we are adding deviations, but the deviations, if any, it will be very near to the merger. Maybe some horizon dynamics and etc., which will probably not.
There are these modified gravity theories. Not that I am a fan of any of them, but people still, work on them and do, simulations and all that.
Yeah.
Is it how possible? Because as you said, that even having the GR waveform is pretty tough. And
Right.
many of these modified gravity theories have more parameters than GR.
Exactly. So there are
is it likely that we would be able to test from the waveforms the different, modified gravity theories?
So there are
say anything meaningful.
Very recent developments along developing numerical relativity waveform modeling using scalar tensor theories. So if we have a very accurate waveform model, then probably we will be able to say something. But until and unless we have a very accurate waveform model, it's very difficult.
Other questions?
So similar to what Chaitanya was asking, so do you have any data constraint on any of the modified theory of gravity from
they are not really being performed on the data because we don't really have a very accurate waveform.
But at least ruling
So
out
it's,
with
we
some
are
of
just,
them, are we able to even rule out some
Um,
of them that no, it's not at all possible?
And or can we
So-
connect these whatever delta phi you are adding to any of their parameters
Okay.
directly?
for example, we do measure the -1 PN term in the gravitational wave data. Now, a -1 PN term can be can come from either massive graviton theory or some theory which gives dipolar radiation. So in that sense, this is so the bound on this is 0.01. I won't say it's ruled out, but the possibility is very low to have dipolar radiation.
So this is just a phenomenological
Yeah.
digression
Right.
from GR, but connect that.
Yeah, only the post-Newtonian theory.
Yes,
Other modified
yes.
gravity.
No modified gravity because the waveforms are not that accurate. So we have modified gravity waveforms at 1 PN, maybe 2 PN. But for GR, we are using 3.5 PN, even in some cases 4 PN accurate waveform models. We at least need waveform models till 3.5 PN to test it against
I
it.
was just wondering whether the extra dimension within modified gravity. So I used to do
The extra dimension, the way we test it is, suppose there are extra dimensions, then the distance, effective distance that we will measure will be more. So in that sense, the gravitational wave speed will be different, the effective distance will be different. From that, we can say that we can provide some bounds on the extra dimensions, but not.
This is kinematics. So in kinematics, by measuring the speed of electromagnetic and gravitational, I think there were some papers that
Yes,
said the
yeah.
dimension is
That way you were
3.
saying. So-
Yes. Yeah.
No, I'm saying this, being inspired.
Mhm.
And those things, actually, in theory, those things also be modified by the formula.
Yes. There are.
Those things are not, cannot be tested like this, no?
No, they can be tested. There are some efforts by the US group, Nico Yunus. So they have a modified waveform model